Today we are discussing the lecture on lab number 6. This week we are focusing on fracture mechanics and the determination of plane strain fracture toughness applied to metallic materials. So the TAs are going to post the video for this experiment next week. In fact, this is a totally new experiment that we hadn't conducted previously, and we managed to have it done just before the closure of the university. So it should be a relatively short experiment in terms of analysis, but we are going to conduct it in order to follow exactly the STM standard protocol. So you have a good idea on how to conduct a fracture experiment using this STM standard. So before we go in the detail of the experiment, what is fracture mechanics? So fracture mechanics is based on the work of Griffith, who sought to explain why the observed strength of a material is considerably less than the theoretical strength. And his idea was based mostly on the consideration of internal defects and singularities formed by cracks in the solid. So the continuum mechanics doesn't apply anymore. And so this will reduce the strength. So Griffith fracture criteria is essentially based on energy. But fracture mechanics is focused on stress intensity at crack tips. So when we talk about fracture mechanics, we discuss three stages in the propagation of cracks, and this falls under what we call the linear elastic fracture mechanics, where we assume that the crack is embedded into a purely elastic material. Of course, in reality, you always have some plasticity or damage at crack tip, but we assume that this damage is confined to a very small zone at the crack tip, and around this zone the material behaves elastically. So the linear elastic fracture mechanics consists in three types of studies. You can look at the crack initiation, usually starting from a specimen that do not contain a crack, and look at how the crack will initiate, mostly from fatigue loading. Then you can look at the fatigue crack growth in the steady state when the crack propagation is established by fatigue from the beginning. So we're looking at the steady state crack growth. And then the last stage represents the catastrophic failure of the material simply in one loading cycle. Okay. So in this laboratory, we are more concerned about the third aspect that relates to the catastrophic failure. However, you'll see that stage 1 and 2 that relates to fatigues are necessary in the protocol to measure the fracture toughness of the material. So why study fracture mechanics? So materials have flows, structures have stress concentration, and this cannot be avoided, but they can be controlled by design. Stress concentration encourages crack growth when the structure is subjected to fatigue loading. Then it follows catastrophic failure, usually after the crack has propagated to a certain length by fatigue. And so these have to be taken into account in the structural design and the material design or processing in order to satisfy the service condition. So overall, fracture mechanics is an important topic that complements the design analysis of the structure. So talking about stress concentration, this is an example of stress concentration from razor. So the razor here is basically a change in the cross-section area of the shaft, and the shaft is subjected to bending. So this is an image taken for photoelasticity, and so the arrow here points to the region of stress concentration. And so in mechanics, from solid mechanics, we can characterize the stress concentration as a stress concentration factor, which is the ratio of the maximum stress in this region divided by the nominal stress applied to the structure. Okay. So stress concentration have had a dramatic impact in the failure of structures. So here are just a few examples, famous example of failure by fracture. So this is the Liberty ship failure in the 1950s here. Crack propagated from concentration on square hatch covers at the top. And due to the hole welded construction of the ship, there were no barriers to arrest the crack propagation, and many catastrophic failure occurs. So this is very dramatic here, where we can see the propagation of the crack through the hull of the boat. Another example in aerospace, so the De Havilland comet in 1955. So they designed here windows with sharp edges. So actually this accident imposed a change in the way we design windows in aircraft for commercial application in particular, where you can see from the corner the initiation of a crack, followed by fatigue crack. So it's zigzagging downward here. And then when the crack became long enough, you see this flat and straight horizontal crack, which is the portion of the crack under catastrophic failure. So if you want, the initiation of the crack was very slow. The fatigue crack growth was a bit faster, but still slow. And then the structural failure was extremely fast. Okay. And a third example, it's the Tim Phillips catamaran from the 2000 case here, showing failure of the left side of the hull here due to propagation of a fatigue crack. Actually, I don't know if it's from fatigue, but it's failed by fracture. And you can see actually the crack propagation at the junction here. So this example is to show that this does not apply only to metallic materials. This structure was carbon composite, and so the problem of fracture applies to other materials than metallic materials. Okay. So who does fracture mechanics? So pretty much any sectors of industry are concerned by this problem. In transportation, especially the aeronautical and aerospace application, where the structures are solicited in fatigue often, and any type of vibration will also promote fatigue in the structure. Structural application like bridge, buildings, and the issue here is these structures are designed to last over decades, and so the propagation of the crack can be very slow, but can happen, and so prediction are important to verify the lifetime of the structure. That includes, for instance, nuclear power plants. Often the aging of the nuclear power plant depends on the aging and damage in the material, the structural materials of the structure. Okay, so here any way to predict the propagation of the crack and when catastrophic failure can be avoided is important. Then we have application in biomedical world, especially implants. Any new materials that's been designed should be tested for fracture mechanics. An example would be in additive manufacturing, for instance. This is an area right now where we know very little about fatigue and fracture in these new materials. And it's different from material we develop with more common technique because we don't know well the macrostructure forming in additive manufacturing. Okay. And then in power generation, so a very famous problem of fracture is in the installation of pipeline for transport of gas, of oil, where a machine during installation will create a defect in the pipe, and under pressure that defect will exceed the fracture toughness or will cause the material to fail by exceeding the fracture toughness of the material. In this case, the propagation of the crack is catastrophic, on the order of kilometers per second. Think of catastrophic failure as a crack propagated as the sound speed, pretty much. So this is a very explosive event, and that will destroy entire mountains. If you are curious and look online, you'll see some example of failure for pipelines that have completely decimated entire forests or mountains. Okay, so this is definitely something to avoid. So generally, anyone designing metallic component for fatigue, pressure vessel, or structural application are concerned by fracture mechanics. So something a little bit aside, but that is important to keep in mind, is before fracture mechanics was invented, so the theory of fracture mechanics has been created in the 1960s, but the problem of fracture existed before this date. And so one protocol that has been used extensively before the 1960s was using sharp impact test. So this is not what we're gonna do in lab number 6, but I wanted to show you a result from this type of experiment. So if you remember from your materials engineering course, a sharp impact test basically is a hammer hitting a small beam on which we created a notch. So the notch is right here. And so we repeat this test at different temperature, from low to high temperature. And during the event, the hammer breaks the specimen. And during this, some energy is absorbed to break the specimen. So at low temperature, it takes very little energy to break the specimen because the specimen is brittle. And then at a higher temperature, it's going to take more energy to fracture the specimen because the fracture is ductile. Okay. And so when you plot as function of temperature, so right now you see a nice, beautiful S-curve. In reality, you'll have just a few data points along this curve, but it will show a transition from low energy to high energy of fracture, of impact fracture, which is associated with a change from brittle to ductile fracture. Okay, and so in this experiment in particular, the parameter we're interested in is the temperature at which the transition from brittle to ductile occurs. Okay, so in this example, it's around 10 degrees C. So I wanted to show you this because when you are comparing the fracture surface of the specimen from the sharp impact test from the low temperature to high temperature, you see a change in the fracture surface. So when the specimen is brittle, it's much flatter than at high temperature when the specimen is brittle. It's not brittle but deformed with a lot of ductility. And in this case, you'll see a more dull and shear appearance. Okay, and so keep this in mind because in the test, it is important to look at the surface of the specimen after failure, because this will be consistent with this picture. So if we see that the specimen has a very flat fracture surface after failure, this will suggest the material is brittle. And then if it's not flat and dull, then the specimen or the material is ductile. And so depending on how ductile you are, the analysis may not be valid anymore. Okay. So in our test, I believe that we're not going to be totally brittle. We're going to be maybe more like in this specimen, so flat and the sides are going to be sheared off. So we'll say that we are in a quasi-brittle regime. Okay. All right. So now let's. So this was for Sharpie. So this is not what the Lab6 will use, because the Sharpie analysis, unfortunately, is not very predictive. It gives you just a temperature, but in terms of design, does not give you any idea of stress or strain, and does not even include really a crack in the beginning. It's just a notch. So in this lab, we're gonna go through the protocol entirely of an actual fracture toughness experiment. And I wanted to show you two types of specimen that can be used. The top one is the what's known as the compact tension specimen. And you can see the pins here with a central notch from which, by fatigue, we're gonna propagate a very sharp crack. Okay, so this is the standard specimen. Now, for some material, it's very difficult to machine this kind of specimen, and I'm thinking here of composite materials or even ceramic materials. In this case, a bend specimen is more appropriate. So you'll have attachment on both sides, and the notch is at the bottom. And usually what we will do here is do a 3-point bending. So it will be attached here, and a wedge will press on the opposite side of the notch to propagate a crack here. So the reason why it's a little bit more appropriate for materials that are extremely brittle, like ceramic material, is because in 3-point bending you have a compressive zone and a tensile zone here, as opposed to this specimen that is only loaded in tension and is purely under tension. So this will break very quickly, as opposed to this one. Now, the analysis of the test with a bent specimen is a lot more difficult and subject to errors. So the compact tension specimen is really the cleanest test for fracture mechanics. Okay, so here we will focus exclusively on the compact tension. So both are pre-machined with a sharp edge notch to initiate the propagation of the crack from the sharp stress concentration. We'll see the design in 1 minute. All right, so in this lab, we're following the SCM standard E399. And so the geometry of your specimen and the ratios of dimensions are constrained. So let me just emphasize a few things. So typically the specimen geometry has a number. So for instance, in our test lab, we use the CT 12.5 specimen. You have other designation. You can find some CT25, CT50. So this number after CT represent the thickness of the specimen, B. Okay? So B represents the thickness. So a CT 12.5 specimen, like in our lab number 6, describe a thickness B of 12.5 millimeters. Okay, so B is important. And then from this you find W. So W will be 2 times B. And so W represents the distance from the pin to the edge here. Okay. And so notice the pin where we're gonna apply the load are located here. And what's important to notice is the crack length A is based on the center position of the pin. Okay, not from the root of the notch. So A is always from the center of the pin to whatever length we find here. Okay. So W represents the total distance from the center of the pin to the end, right? So you'll see the ratio A over W is what is used in the formula to compute the stress intensity factor. So why is this geometry used in fracture mechanics? Well, you can demonstrate that with this geometry, the localized plasticity is very small at the crack tip, and all the deformation is mostly elastic. So this is what is called a compact tension. It's because it's very limited plasticity, and therefore this geometry fits perfectly with the linear elastic fracture mechanics theory. Okay. So important parameters will be W. So A over W equal 1 means your crack has propagated through the specimen. Okay. And so we'll start with the pre-existing crack length. It will not be 0. Alright, so in your lab report, you're gonna compute the fracture toughness, which is the critical stress intensity factor at which the crack produce catastrophic failure in one cycle. So the ACM standard provides you with a formula. So this is something you will have to program probably in an Excel spreadsheet or MATLAB or Python. Let me just explain quickly the formula. So this is K, the stress intensity factor in mode 1 loading. That is, we're in opening mode. So opening the crack here in tension. P is the apply load. W is the width I mentioned earlier. Okay, so that's W from here to the end. Then we have square root of B times Bn. So usually instead of the square root, you just have B. So the text of your Lab6 will have just B. So what is this Bn? So for some specimen, so that's not our case here, but some specimen we create some groove on the side of the specimen to make sure the crack propagates flat and horizontally. Okay, so there's no bifurcation of the crack when it propagates. But usually I don't like this technique because it creates an additional stress concentration on the side. So it's just better just to leave the crack grow as it likes, especially if the grain size is large. You'll find that the crack does not propagate flat because the grain is too large. Okay. So for most of the time, I would say 95% of the time, B equal Bn. So Bn is actually the thickness of your specimen. So if B equal Bn, then square root of B square, it's B. Alright, so this term is B, square root of W. Okay, and then F, remember, is the shape function. So usually F is close to 1. And so for the compact tension specimen, the recommended value is given here. Notice its function of A over W is adimensional. It's a polynomial function. Now there are different formula you can find in the literature for the compact tension specimen. But this one is the recommended formula from the ASTM standard E399. Okay. So the parameters that are known in this equation, at the beginning of the test, you can measure the thickness B, the width W. So these are imposed by the design of the specimen. You apply the load P, so you're controlling that, and you will have to measure the crack length. So typically, while we're doing these experiments, we are going to estimate the A here to start with, then increase the load until it fails, find the critical load. So PQ means it's the critical load at which we have catastrophic failure, and I explain the method to determine this load. And then after the specimen is broken in two halves, we look at the surface and we'll see the transition when it went from fatigue to the fracture toughness experiment. So we'll be able to measure A after the test is completed. Okay, so the technique is really finding P, and then after the test measuring A and plugging this into this equation to find the fracture toughness K1C. So in fracture mechanics, we're discussing three types of methods. We can use fracture mechanics to study the fatigue crack propagation. In this case, we'll be measuring the change in crack growth rate, fatigue crack growth rate, dA over dN, n here represents the number of cycles in fatigue, as a function of the stress intensity factor range, delta K. Okay, so that relates to fatigue. So we're gonna start with doing some fatigue in the test, but we are not going to measure in this lab this dA by dN versus delta K curve. But it could be done. But we're not gonna focus on this aspect. We're gonna focus on the second aspect, which is the fracture toughness. And we're gonna assume here that the material is quasi-brittle because you operate at room temperature. However, because we are testing aluminum, which is a very ductile material, we may be borderline here with this theory. Okay, so maybe aluminum is not the best material to test the brittle fracture mechanics, but the analysis is a little bit more simple than the second one. So if your material really exhibits a lot of ductility, especially if it is tested at high temperature, then in that case, we will use another technique called the J1C analysis, which is based on the J integral theory. So there is a relationship between J1C and K1C. But the protocol is a little bit more complicated, and so we're not gonna do this in lab number 6. Okay. Okay. So here's just a view of a compact tension specimen after the test. And so what is important to understand is in the same test, we're actually conducting the crack initiation. So we have a notch. In fact, our specimen in lab number 6 will have a V notch here, a chevron notch, to properly initiate the crack that facilitate the crack initiation. So there's a crack initiation, then we propagate in fatigue, here the red region, and then we stop the crack in fatigue and apply the monotonic load to break the specimen, and that's from this test that we are measuring the fracture toughness. So if you know that your material is brittle, then the K1C analysis is what's used as a method. And if you know that your material is going to be very ductile, so if the test is performed at high temperature, for instance, then J1C analysis will be more appropriate. Okay, so in this test, lab number 6, this experiment, we are using only the K1C analysis. And then how do you apply this this data? So why this fracture toughness is important is because it's based on the stress intensity K, and K is independent truly of the structure. So basically, your fracture toughness in terms of stress intensity should be exactly the same regardless of the shape of your material or structure. So if we can establish it on the compact tension specimen accurately, then the same value should apply to any structure. So that's an example here of a shaft that has failed. There was a flaw here in the shaft. You can see here the fatigue crack propagation. You can see those marks here. They are basically based on striations on the macroscopic scale. So this defect generated a fatigue crack, which propagated up to a certain point, probably around here, and then the region here fell in one loading cycle. Okay, so technically, in theory, the entire area is designed to sustain the load applied to the shaft, but because of the propagation of the crack, even though this ligament here should have sustained the load, the fracture mechanics led to failure of the parts by catastrophic failure or propagation of the crack here. Okay, so knowing the stress intensity at which the crack will propagate in catastrophic mode is critical for the prediction of the shaft here. Okay, for the lifetime of this part. All right, so now let's just focus in the time that's left on the experiment itself. So this week's experiment, the goal is to measure the plane strain fracture toughness K1C of an aluminum alloy 6061 following the STM standard protocol. The number is E399, which is provided on Blackboard. And I strongly encourage you to read the this protocol. I mean, not the protocol, the STM standard. Okay. So what are we defining here by fracture toughness? So from a material standpoint, it's the ability of your material, in the event it contains a crack, to resist fracture or resist the propagation of this crack. So here we make the assumption that there is a pre-existing crack which has been initiated and propagated by fatigue and has attained a certain length. And so we want to know what will be the stress intensity that produce the critical propagation of the crack under constant load. Okay, I mean a monotonic load. Now mathematically, from quantum mechanics, from fracture mechanics, this will be the critical stress intensity factor above which a crack propagates, and would be under the assumption that the behavior is quasi-brittle. Okay, so this theory only apply for brittle fracture. So when the stress intensity factor in this geometry exceed the fracture toughness K1C, then we have catastrophic crack growth. Okay. Alright, so let's go in the specifics of our lab experiments. So we design those specimens for the lab out of a rolled plate of aluminum alloy 6061 T6. These specimens have been made by Floyd Villemont in the machine shop at UVM. So it's very hard to obtain these specimens online. And so we actually made them in Voti. And so this is the sketch of the specimen that has been designed by, machined by Floyd. So the dimensions are very important here. Okay. So you see here your W is 25 millimeters. All the units are in millimeter here. The thickness is 12.5. So that's why it's called a 12.5 CT 12.5 specimen. But your W is 25. The total length is 31 millimeters, so it's not very big. And what is important here is the notch we form is at 5 millimeter precisely from the pin. So we're gonna look at images. You'll be provided with images of the crack after propagation in fatigue before we perform the K1C test. And this picture are taken from the root of the notch. So remember that the actual crack length, if you're measuring the crack length from the notch, you need to add 5 millimeters to ensure you get the proper crack length from the center location of the pins here. Okay, so that's one aspect. So the thickness is 12.5, and then the way we design, so that you can put basically the crack in different directions. So it's very important to know how you orient your specimen during the machining process. In this lab, we decided to look at the longitudinal crack propagation. So it corresponds to this TL configuration. All the specimens have been made in exactly in this direction. So the crack is parallel to the longitudinal direction L, and T represents the transverse direction. So we use a TL configuration, TL direction. So here I'm holding one of the specimens. Now you note that in addition to the notch, we have another notch here that is used to attach the cracked mouth opening displacement gauge. And that's important in fracture mechanics because we will be measuring the opening of the crack as we apply the load as a way to measure the fracture toughness of the material. This is a schematic from the E399 standard. The gauge looks a little bit like your extensometer. In fact, it works, instead of working in tension, it's working in compression. So these act as these two cantilever beams act as springs that are in direct contact with this notch here. Okay, so our specimen has this notch design, so we can attach directly at the mouth of the crack. So for us, the crack here is right here. Okay, remember that the crack is actually measured from the pin center. So we are not directly under the center of the pin, but that's good. It's not gonna affect the measurement at all. All right. So when we open the crack, this is going to measure a positive opening from this position, and then it works as a standard extensometer or like a strain gauge. It will be measuring a resistance. We have a quarter bridge setup, so pretty much like your strain gauge experiment in lab number I think that's lab number 2, where we collect the strain from the deformation of the beam here. So let's talk about the alloy. So this is an aeronautical aluminum alloy. It's aluminum with a small amount of magnesium, and so this contributes to the strength of the material at relatively higher temperature than room temperature. So aluminum has the low melting point on the order of 600 degrees C. So it's not considered high temperature material, but by adding magnesium to it, we can raise this by maybe a few hundred degrees. So for hot parts, or if you have a cover in your jet engines that's made out of aluminum, then these materials actually, their strength remains relatively high even if you heat them a little bit. And they are also, their performance in fatigue is quite good. So the composition is aluminum, magnesium, then the other elements are just there for microstructure. So silicone contributes also to the high temperature properties of the material, I mean, by high temperature, I mean intermediate temperature, something on the order of maybe 100 or 200 degrees C. Okay, but nothing very high. And the magnesium is usually used as a way to maintain or keep the microstructure constant. All right, so in your lab, you're gonna need some information about the tensile properties. So the tensile properties were extracted from this journal article from Jogi, and provide you the elastic modulus, the yield stress, the ultimate tensile strength, and the percentage of elongation, which is a measure of the ductility. So you see it as some ductility, 22%. So it's not totally brittle. It's actually more ductile than brittle. And so the parameter you're gonna need in the analysis is gonna be the yield stress. You will see why. It's one way to verify that your K1C analysis is valid. Okay, so the parameter you need is going to be the yield stress here. All right, so the protocol. So again, we'll follow exactly the protocol from the SCM E399 standard. Consists in the following. So next week, the TAs are going to post the video of this experiment. Okay, and it consists in the following. It has a stage of crack initiation. So we put some markers on the side of the specimen at 5 millimeter from the notch. So actually, there's a bit of a typo here. It's not the crack length, but it's the distance from the notch. So you should add 5 millimeters from this value. So up to 5 millimeter, and then another one at 10 millimeter. So the actual crack length will be 15, 10 plus 5. And here the actual crack length will be 10, 5 plus 5, 10. Okay. So the first stage, we do crack initiation. So this process is usually requiring, about 50,000 fatigue cycles. So what we do is we increase the load. So we have about a low stress amplitude on the order of 6 kilonewton at 20 to 40 hertz. I think we choose 20 hertz in our experiment. And second stage, once the crack propagates to about 5 millimeter from the notch root, we slow down a little bit the fatigue crack growth. So we reduce in amplitude to 4 kilonewton at 5 hertz or 10 hertz to achieve a steady state crack growth. So it's clean, and we have here a stress intensity factor range that's more in the range of 10 to 20 megapascal root meter. And so we propagate up to about 10 millimeter from the notch, and then we perform, so we stop the test and then perform the K1C experiment, from which you will find the data for your lab report. So we apply a monotonic tensile force until failure. We collect the force and the crack mouth opening displacement versus time. And so this is the results that will be posted online, along with images of the crack on the side of the specimen before we perform the K1C experiment, and a picture of the fracture surface of the specimen after we fail the specimen. So this is performed in VOTI 246 in our clean materials lab, using the Instron machine, the same machine that you have used for the tensile testing, except here it's equipped with a special fracture mechanics grip called Clevis grips. So they look like this. Here's your CT 12.5 specimen. You can see the marks the TAs have made at 10, 5 millimeter, and you see the crack mouth opening displacement gauge from Instron that's clipped on the notch in the specimen. So how do you determine the K1C? So focusing on the final stage. So we'll be collecting the force and plotting the force versus the crack mouth opening displacement measured from the strain gauge. And the curve is could have different shape. So the standards give you how to measure the maximum force. So the technique is as follows. We'll focus on type 1, which is more representative of the actual experiment. So in your test, you're going to use the 95% slope method, which consists in measuring the slope of the linear portion of the curve. So don't go too far because the curve becomes very nonlinear quickly, and avoid using the initial nonlinearity of the curve. So you exclude a few points in the beginning, but you use the most linear portion of the curve here, measure the slope, and then draw another line with a slope reduced by 5%. So it's the 95% slope. And then the intercept gives you a load PQ. And that's the load that you will use in the formula of your K1C. So KQ is the stress intensity factor at this load PQ. Okay. Now, depending on the shape of the curve, if your maximum happens before PQ, then it's possible you have to do some adjustments. So like type 3 here, PQ is in fact Pmax because the max happened before the sequence. Okay. So it would be one of those three cases, right? In this case, the max is after, but there was a secondary maximum before the intercept here. So in this case, PQ would be the secondary maximum. But I would say that type 1 is more representative what you should expect from this test. So in order to compute K1C, we need to have the crack length. So the standard asks you to take notes of a lot of information. So information about the specimen dimensions, the pre-cracking, how in terms of stress intensity factor, what load and stress intensity factor have been used to do the pre-cracking, because we want to make sure we did not overload the specimen before we reach the K1C experiment. But the most important part is this part here, this top right corner, the pressure test. It's about the crack size. So after the test is performed, you're gonna have two pieces of specimen. And so we look at the surface of the specimen to identify the crack. And so there are three measurements that you need to make. One is in the center of the specimen. It's noted as 1 here. And the other two are a quarter distance from the side on the left and right. So 2 and 3 in this image. So here's an example from our Lab6. And this is our actual specimen broken. You can see here the crack initiation, the 5 millimeter marks here, then the 10 millimeter marks here, and here the dull part is actually our K1C experiment. Okay, and so here we are seeing a top view, and this is the image you're gonna need to analyze in your test. So we know the thickness of the specimen, which is 12.5 millimeters. So that gives you the scale for this image. We don't need to add a scale here. And remember, this is the notch root starts from those points. Okay. And so you're going to make 3 measurements. One will be in the center of the specimen. So this is your crack before the K1C experiment here. This is the 5 millimeter mark. This is the 10 millimeter mark. We take the 10 millimeter mark. So you'll need a measurement of A from here to the center. And then you take 2 points at a quarter distance from the side. So take the center, take half the distance, and measure this. So you take 3 crack length measurements. So center, left quarter distance, right quarter distance. And take the average, and this constitutes your crack length in the formula to compute the stress intensity factor and the fracture toughness. Okay? So load is from the 95% slope method, and crack length is from direct analysis of this picture. Alright, so just one more slide to conclude. We are focusing on the plane strain fracture toughness. So if your specimen becomes very thin, what is happening is the fracture toughness will become dependent on the thickness. So in terms of design, this is bad because now we have the geometry impacting the fracture toughness of the specimen. So truly, what we want is a constant value, and that's what we call the plane strain fracture toughness. And plane strain means that the specimen is thick enough so the fracture is flat. Okay. So how do we verify that we have a plane strain fracture toughness? In the last stage of this protocol, once you computed your K1C value, you're gonna use this formula 2.5 times the square of K1C over the yield stress of the material. Okay. Calculate this value, and this value has to be smaller than the actual thickness of your specimen. So from this, you can determine whether your experiment of K1C was valid or invalid. All right. So this concludes this week's video lecture for lab number 6, and the results, pictures, force versus CMOD displacement result will be posted online, and the TAs will post the video of Lab6 experiment. Thank you.